proving the alternating series test, which is a really powerful test for the convergence of sequences, which basically tells you that if you have an alternating sequence, this is how we make it alternating, -1 to the power of n plus 1. It's to the power of n plus 1 so that, the first term is positive. It could also be to the power of n minus 1. But if you have a sequence like this, where the terms are, alternating, so we have b1 minus b2 plus b3 minus b4, so they're alternating. And if every term is positive, and if this series is decreasing, if the sequence is decreasing, so bn plus 1 will be less than or equal to bn, so every next term is smaller than the previous term, and it converges to 0, then we can say that the sequence then we can say that the series converges. So the sum of the sequence converges. And why is that kind of powerful? We have the classic harmonic series, which is the sum from n equals 1 to infinity of 1 over n. That's a classic harmonic sequence, and we know that that's divergent. It goes to infinity. However, if we look at the alternating series test, if we have the sum from n equals 1 to infinity of then -1 to the power of n plus 1 times 1 over n. Well, all of a sudden, this is an alternating series. 1 over n, of course, it's always positive, and of course, it's decreasing. So this actually converges. So wow, that's kind of, the normal case diverges, but this case, if it's alternating, it converges. So, it's a pretty powerful test. It's a pretty powerful test. It allows us to do that. And how we're going to prove it? There's two ways to prove it. One with the Cauchy criterion for sequences, but we're actually going to prove it using the Monotone Convergence Theorem, which is this guy over here. It basically says if a sequence of real numbers It basically says that a sequence of real numbers converges if it's monotone. So if it's either increasing or decreasing, which means either each term is bigger than or equal to the next, or each term is less than or equal to the next. So either it's always increasing or it's always decreasing, and it's bounded. So there exists a supremum and infimum, and if these two, so if it's decreasing and it's bounded from below, then we know it converges to its infimum. And if it's increasing and it's bounded from above, then it converges to its supremum. That's what the Monotone Convergence Theorem says. And we're basically going to split this series into two series. So we're going to split it into the even series sum and into the odd series sum. And we're going to show that they converge to the same value. So then we're also going to show that the normal series converges to that value. So first of all, let's look at the even partial sums. So basically, we're turning this series into a sequence by looking at its partial sums. We're looking at the partial sums S2k, and it's 2k because because we say it's even, we're always summing up an even number of terms. So if k is 1, 2, 3, this is going to be 2, 4, 6. So this way, by saying 2k, we're always summing up an even amount of partial terms. So let's say if k is 3, we're going to have b1 minus b2 plus b3 minus b4 plus b5 minus b6. So we have this, and it can go on and on for longer if k is bigger. But this is just our sequence b, and this is our partial sum s2k if k is 3. And now first we got to show that it's increasing. So basically, if we show that this is increasing, and if we show that it's bounded from below, if it's bounded from above, then by the monotone convergence theorem, we can say that there exists a limit to it. So how do we show that it's increasing? Well, just by grouping the terms together a smart way, just by using parentheses in a smart way, we can see that since the sequence is decreasing, we know that b2 will be less than b1. We know that b4 will be less than b3. So we know that all of these terms are going to be greater than or equal to 0. And so, now we can obviously see that, of course, the sequence is increasing. We just keep on adding positive terms. If we increase k to 4, then we're going to add, we're going to have plus b7 minus b8. This is adding in, this is basically adding an extra term to our sequence. If k increases by 1, we're going to get 2 new terms. This is also greater than or equal to 0. So, this will be bigger. S2k plus 1 will be bigger than or equal to S2k. So we just showed that it's increasing. Now we gotta show that it's bounded from above. Well, how do we show that? Again, another smart way to group terms. Now let's imagine we have S2k equals b1 minus b2. Now I'm gonna group it in such a way, actually, so you're gonna see b1 minus b2 minus b3 minus b4 minus b minus minus b5 minus b6. So this is the same thing as this. I just grouped it in such a way. That's b1 minus b2 plus b3, it's just a different grouping. But now we can see that, this is our first term, b1. This is greater than or equal to 0. This is greater than or equal to 0. All the groupings will be greater than or equal to 0. And this final term, it's just a term. It has to be positive by, this. So this is also greater than or equal to 0. So S2k will be bounded from above by b1 already, for example. Here we show that it will be bounded from above by b1. So it will never be greater than b1. Because, if we just add new terms, we're going to add new groupings, which are just going to subtract away from b1, which means that, as k goes, as k gets bigger and bigger, we're just going to keep on subtracting positive terms away from b1. So it's bounded from above. And now, so basically, S2k is less than or equal to b1 for every k from n. From n where k is greater than or equal to 1. Our sequence starts with 1, so obviously. So we showed that the even partial sum is increasing, and we show that it's bounded from above. I'm trying to write really fast. So there exists a limit, and we can call that limit L. So the limit as n goes to infinity of the sequence S2k. This is a sequence because it's partial sums. It's the partial. When k is 1 is the sum of the first two terms, and the sum of the first four terms. The sequence has a limit, and we can call this limit L. Now let's look at the odd partial sums, and we're basically halfway done with the proof already. Odd partial sums. Now we just got to do the same thing here, but here we're gonna see that the odd partial sums are actually decreasing, and they're bounded from below. So basically, what we're gonna show, I'm just giving a little spoiler here. This is, let's say this is 0. We have our limit L. So let's say our sequence converges. Let's say our series converges to this limit L. Well, then we're gonna have terms like this and terms like this. So basically, this will be the odd series of partial sums will be decreasing, and the even series are going to be increasing, and eventually they're going to meet at this common limit L. This is what we're going to basically show. So the odd partial sums, well, let's look. Firstly, we denote odd partial sums by saying S2k plus 1, because 2k plus 1, this always, for any k, this gives us an odd number. So now again, we just write down the first few terms: b1 minus b2 plus b3 minus b4 plus b5 minus b6 plus b7. So, before we had up to 6. Now if we add a 7th term, then all of a sudden this sum becomes part of our odd partial sum. So all of a sudden, before it was an even partial sum, now it jumps to an odd partial sum. Well, now again, how do we group the terms if we want to show that it's decreasing? Well, we'll just group them like this: bang, bang, bang. Well, b2, b3, these are all positive numbers. b4, b5, these are all positive numbers. So we have b1, and we just keep on subtracting positive numbers here. This is greater than or equal to 0. This is greater than or equal to 0. We keep on subtracting positive numbers from b1. So obviously, we see that, if we add more terms, we're just going to decrease it further. Basically, we can write S2k plus 1 equals S2k minus 1 minus b2k minus b2k plus 1. This is, you can check that this is true, but basically, just by kind of looking at the terms, this holds. So basically, we can see that S2k plus 1, is going to be smaller than its previous successor, S2k minus 1, by this, positive thing that we subtract from it. So we just show that it's decreasing, and now we got to show that it's bounded from below. And this one's kind of the hardest, but it's still pretty easy. You kind of got to do it in a smart way. There's multiple ways to do this, but how we're going to do it, we're going to say S2k plus 1, well, that just equals S2k plus b2k plus 1. Like in our example over here, S2k plus 1, this just equaled S2k, and then you add, it went up to 6 S2k, so if k is 3, and then we just added another term, so just S2k plus 1 is the partial sum up to k terms, which is even, and then we add one more term, and that makes it odd. So we have this, and now we can say that this is greater than or equal to S2 plus b2k plus 1, because obviously we showed that the even partial sums are increasing. So obviously, for any k that's greater than or equal to 1, for example, if k is 3, S6 will be greater than S2. So, this term stays the same, but this term will be bigger than S2 for any k that's greater than 1, because we just show that the even series is increasing. So this is true. And what does that equal? Well, S2 is just B1 minus B2 plus B2k plus 1. So S2k plus 1 will always be greater than or equal to this. So as k goes to infinity, since our series goes to 0, this is going to go to 0. But B1 minus B2, this will always stay the same. This is a constant, and it's greater than or equal to 0. So even as k goes to infinity, S2k plus 1 will always be greater than this over here, so it is bounded from above by b1 minus b2 here, is what we showed. So it doesn't converge to b1 minus b2, but it's bounded from above by it. It will always be, it's also bounded by above by numbers smaller than b1 minus, by numbers smaller than this. But we just showed that it is bounded from above. And now, so the beautiful thing is it's decreasing, it's bounded from above. So also by the by the Monotone Convergence Theorem, there exists a limit. So the limit as k goes to infinity of s2k plus 1 equals, before we called it L, now we can call it M. But we're going to show that, L equals M. And how we're going to do that, this is the final part of our proof. Now we got to show that the two limits are equal. Well, this is the easiest part to do. The limit as k goes to infinity of s2k plus 1 equals the limit as k goes to infinity of s2k plus the limit as k goes to infinity of b2k plus 1, because s2k plus 1 is just s2k plus the next term, which is b2k plus 1. So the limit as this goes to infinity is just the limit as this goes to infinity. We show that that both limits exist. We have to, by showing that they're decreasing and bounded, we show that both of these limits exist. We have to do that. And now as k goes to infinity, since in our initial statement we said that our sequence bk goes to 0, bk converges to 0, so that this just goes to 0, which shows that at infinity these two limits are going to be equal. So we call this limit M, we call this limit L. These two limits are equal, so the even and odd terms converge to the same limit, which means that also, if you think about it, if the even part of the terms converge to the same limit, the odd part of the terms converge to the same limit, then the only way that's true is if the whole sequence converges to the same limit. So we just showed that the limit over the limit as k goes to infinity over partial sums converges, so that limit as k goes to infinity of sk equals L. So there exists a limit, which means our sum, the limit of the partial sums is convergent. That's exactly the definition of saying that the sum is convergent. So we just showed that we just finished the proof by showing that, and the proof of the alternating series test, which shows that any sequence where these criteria are satisfied converges. And there's also a cool thing you can do with the error bound, and I already kind of gave this away with the graph. If we imagine this is 0, this is our limit L. If you imagine our partial sums, they're gonna go like this. These are all the partial sums. These are all the odd partial sums. So this is S1. Like maybe this point's S1. This point is S3. This point is S5. And then these are all the even partial sums. So this is S2. They're increasing. This is S4. This is S6. Well, our error, we can show that our limit L will always be between two partial sums. So L is less than or equal to S2k plus 1, and it's greater than or equal to S2k. And we can clearly see this here. L, which is our limit here, will always be between the odd and the even one, the odd and the even one, the odd and the even one. Even as it gets infinitely close, eventually, this will just be equal, because the odd and even partial sums have the same limit L. But you can kind of see how nicely the error is bounded between S1 and S2, S3 and S4. The limit will always be bounded here. And yeah, that's the end of the proof. That is it. Hope you enjoyed, and thank you for watching.